This module provides a brief overview of altimetry, an active remote sensing technique used to estimate sea surface height, including significant wave height. Over long periods of time, altimetry data can be used to observe changes in sea surface height caused by anthropogenically forced global warming as well. Altimeters transmit at nadir toward the surface, and we are interested in knowing the time delay between transmission and receipt of the backscattered return if we want to compute sea surface height. The pulse width is very short, and the remainder of the time between transmission and return is spent listening for the return signal from Earth. This takes roughly 4 to 5 milliseconds, then a new transmission occurs. Given a known speed of light, the time delay tells us the distance between the satellite and the surface. Variations in the ocean topography can be caused by many factors. Tides or atmospheric conditions can alter the surface. More importantly, though, the uneven distribution of mass in the planet impacts the gravitational pull globally, which also alters the mean sea surface height. The topography of the ocean surface, given Earth's gravitational field, is known as the geoid. This is essentially the background ocean topography in the absence of any other forcing. In order to estimate the sea surface height to the intended accuracy of 2 to 3 centimeters, the geoid must be known as accurately as possible, and the height of the satellite must be known exactly. The latter can be constrained using GPS, while the former has been mapped during several prior missions. The H on the Earth, shown in this slide, represents a region with a higher geoid. Therefore, we would expect the typical time delay here to be smaller, and we need to account for this when determining sea surface height above the background state. The geoid relative to some reference ellipsoid shape is shown here. And so the geoid is this kind of undulating bold black line, and the reference ellipsoid is this thinner black line down here. The satellite orbit parallels that way up higher, and then the actual sea surface is this dashed line. The undulation of the geoid is the variation between it and the reference ellipsoid, typically about 60 meters or less. The sea surface height, denoted by the dashed line, is the variable of interest, and the time delay to it is what is measured by altimeters. The difference between the sea surface height and the geoid is the topography. Orbital characteristics for one altimeter, JSON 3, are shown here. Note that the orbital altitude is higher than most other low Earth orbiting satellites we have discussed in class. This is because at lower altitudes, even slight drag will cause the orbital height to deviate more than is acceptable to achieve 2 to 3 centimeter accuracy. And as we'll mention again briefly, notice how the repeat cycle, or the return time, is very low, very high, about 10 days. So the temporal resolution is not very good. Other information can also be garnered from altimetry data. Ocean floor topography can translate to detectable sea surface topography, and ocean surface currents can be deduced as well. Another variable provided by some altimeters is significant wave height. It is the average height of the largest one-third of waves. Altimeters can deduce wave height by considering the length of time that a return pulse takes to fully reach the receiver. For example, take the drawing at bottom left for a hypothetical wave of some height. It is the average height of the largest, For this single wave, the altimeter will receive its first signal in the time that it takes for the signal to travel to and back from the top of the wave. However, the entire backscatter from the wave is not received at once, or even within the time that the pulse was originally emitted, though. Signal that reflects off the bottom of the wave will take a little longer to reach the receiver in space, therefore lengthening the return signal. Let's suppose that time in this small wave is delta t. If we double that time, then we are doubling the likely wave height. A daily composite of significant wave height derived from several altimeters is shown here. Notice how much of the surface, all these white areas over the ocean, is unobserved even when using several sensors simultaneously. This is because altimeters only scan in a narrow region directly beneath the satellite. This is only one example of a data product publicly available. But if we zoom in with this on Okinawa at the same time, we see significant wave height along the swath passing over the island. Heights range from near zero, 1 to 2 feet or so, to near 10 feet along the swath seen in this image. They are represented by the blue and black numbers that could be different colors if the wave height was larger. The colors of the numbers alongside the image in this example, such as 0147, indicate that the satellite that made the observation, such as in this case down here, and the number represents the time of the observation.